My talk today is about how 3D vision and also AI can help us actually to reduce the effort when you want to set up a 3D vision solution, which is key because we don't have so many experts in the field that can really deal with these complex scenarios, and this is basically the scope of my talk today. Why are we doing 3D vision? This is a bit of the motivation. Many of the applications that we see today with robots are still kind of non-flexible. So the robot is actually a universal tool, but it becomes only flexible with vision and the gripper. And with the 3D vision part that we are motivating, you can really work on having not such exact feeding anymore. You can go from the bin and set up directly from the feeder. So there's a lot of applications that are enabled when you use 3D vision in your application. Also, small changes in your production can lead to larger downtimes, so you don't really have the flexibility. What we are proposing basically in the beginning, usually you have parts in fixed locations, you pick them up, but what you actually want to do is you have them in an unordered state or you have in a mixed state. In order to solve that, the feeder, mechanical feeder, is potentially not the right solution to that. This is why we say that 3D vision, which gives you a metric scale on the part, actually helps you in combination with the robot in order to push that forward. I said it already, so 3D vision combined with machine learning actually can make the robot smart in a sense that it enables the flexibility that the tool itself can do. So of course the gripper also plays an important role. I'm focusing today on the vision side, but here we really can bring benefit, especially when you talk about machine tending. A lot of vision systems are deployed, and especially in the second case when we go into the logistics domain, the vision system is actually the key enabler to enable robots to work in this domain, because there we have a lot of parts that we actually don't know. So here a robot without vision is actually not being applied. So this is why we see a strong need here to bring more 3D vision systems together with robots. Just give you a bit of an overview here. So we have two domains that we are covering. The industrial automation, automotive. So here the classical approach is to use mechanical fixtures. There you have a lot of individual engineering. You have a small amount of different parts, but the big benefit is you have model data. Drawback is you have to do pick and place, so actually you have to think the process from the end where the part goes. 3D vision can help you here to remove the fixtures. You can have a more flexible design. You can pick from the bin directly, for example, which saves you a lot of shop floor space. The model-driven approaches that you can use here, they require a model, but a CAD model is there, so you can use it for the training. That basically reduces a lot the on-site training time, because you have it based on the model. And model data that you have, you should use in your process. And you can combine nicely here classical methods that enable you a lot of robustness, right? For the place, you need accuracy. Machine vision or basically machine learning usually gives you errors in percent, but you want to aim at a millimeter or something like this. So if you combine here machine learning together with classical approaches, you actually achieve the accuracy that you need. In logistics, it's a bit different. So here we have a lot of high cycle time. We have a lot of different parts, and the objects are usually unknown. Unknown in a sense, we don't have a model of them. It's pick and drop. That makes it a bit easier. But basically, the challenge here is the unknown part and the high cycle time. And this basically tells you that you have to use vision here in order to enable this application. Here you of course have to bring some data-driven approaches in, but still you can use some model data to make the training and the data recording less intensive, because that's actually a problem to generate all the data, work on that, label it accordingly, and so on. And here we will basically see that it's a combination with model-driven and classical approaches as well that can actually lead to success. Bringing that to the topic, 3D vision and applied AI is actually the thing that enables the flexible production. What we are doing on that side, so we are dealing with smart sensors. So you can see a little bit our product portfolio here. So we have stereo-based systems. They all have an onboard GPU, so we can actually run software on the camera directly to enable for these applications. We have a couple of applications up there. So we are working on the commissioning picking, we're working on depalletization, but also on machine tending with silhouette match and CAD match. And each of these modules can basically activate it on the sensor. So you do have the same hardware, but we use it for different applications. So you don't have to switch the hardware in order to do a new application in the field. Yeah, and then we have also the possibility to deploy off-board, and I will tell you a little bit more in the future in this talk why this actually helps to bring the application to success. Why are we using stereo? Stereo is a technology that is greedy, so you need to have computing resources, but also machine learning is greedy, and with the success of more performance in embedded computing, this actually becomes much more feasible. So it used to be that you had to have an FPGA and all that very special stack. You can do this on an onboard GPU, on an embedded Jetson, something like that, and then you have more flexibility to actually bring such a solution to the market. Big benefit of stereo is also you have images which you need for the machine learning and the depth data in the same time frame, right? It is calibrated on the same system and you have the same data at the same time. So you don't have to synchronize a laser with a camera, a time of flight with a camera. It's all recorded at the same time, in the same time. So it's much easier to bring the data together later on. And as I said, depth is needed for the picking. Images are needed for the machine learning, so you can combine these two approaches together to make the best out of both worlds in this combination. At the moment I see three major trends in robotics, and I will list them in the following and have a little bit of an elaboration why we think they're important and what could be a potential solution here. The first one is good data, not big data. We're working in robotics. Actually, that's not really big data, so we still have limited data. And the question is, how do we get the right data to solve our case, to have actually this data set that we need? Yeah, so one thing is that a lot of time at the moment goes into labeling of data because someone has to do this. So basically, if you have a data scientist, usually that's not a roboticist. So he's basically labeling the data based on the vision side. But in the end, it's about a physical process that you have to do with your robot. So the robotics expert is usually not labeling the data, and so you have to connect the two. What we are basically proposing here is that, especially in machine tending, you have models, you have CAD models, you can use them in the simulation to generate your training data, and the big benefit is you don't have to do this on-site, you can do this offline ahead of time, and you have ground truth, because in a simulation you know where the part is actually really situated and not someone has to take it out of the data. So this is a big benefit when you work with CAD models and machine learning for especially bin picking applications. What can we do in simulation? So just some examples here. So usually we ask for the CAD model. We can put the CAD model in different scenarios, in bins, on tabletop scenes. We can change the material. We can basically include the sensor properties such as blur, noise in the image, and can run this through in simulation. We can turn on the light. We can turn off the light. So we have everything in our training data set on ground truth data. Of course, what we don't have in the simulation will not be trained. That is also clear. But the question is it really so much that is missing for a classical machine tending or bin picking application? Here you can see a small example how this actually looks like. So we have to the left simulated images based on the simulation. Then we can have a simulated point cloud. This is what we can use then also for the point cloud refinement and later on. So we have all the data available. And we can basically determine based on the simulation the potential accuracy that we lead to. Because ground truth data is there, we can perform the detection in the virtual world and see what comes out. So that's basically, as it's simulated, it's the best case. But if you already in the best case have a scenario where you have a huge deviation, that's potentially not a bin picking project you want to do. So you can do the feasibility of the case quite early in the process. If there's doubt, of course, you check on the data in more depth. But at the beginning, you have a very early access saying this is going to be working, this is not going to be working, here I need more information. So you have an early check what works and what doesn't work. Yeah. how do we deal with unknown objects? Also an example that I'm bringing here. So if you don't have object data available, the system should generate it. So what we are doing here is basically we're using a solution where we check what has been picked. So basically we have an assumption what's in the bin. We are saying we're looking for grasp points with a suction cup, so that doesn't work with a two-finger gripper, but in logistics it's mostly suction. We pick it out and afterwards we see what we took from the bin. And this is basically a match that we can take out of the scene and generate on the fly the model. So you could call it an auto labeler, so to say, because actually it considers the part that you picked. And then you can use the depth data in order to generate these object views. The more object views you generate over time, it's not really machine learning in that sense, it's self-improvement, I would say. But you start with no knowledge about the part and you generate it over time. And this helps already a lot to have robust picks of the system. What you can see here is basically in the beginning we just detect the load carrier, then we are matching the surface, we're doing the identification and can compute the grass on top of that. If the part has never been seen before, then basically whenever you see these parts look like that, they are more or less already having a match available. For the other ones, it's not the case. So basically, whenever you have already a representation and a view of the part, it's considering that and it's improving the grasp on that one. So here we have the possibility to really improve based on the data that you see after a successful pick. Yeah. So that's basically just improvement over time. And this data generates you the database of the objects that you'd actually seen. The second trend, plug and produce, also very important because in most cases you are dealing a lot with software, and the software has to have a clear deployment concept in order to be updatable, extendable, and so on. Because once you deployed the software, you don't want to start all over again when you have to do an update. The customer comes for that. I know in robotics usually people don't update so often their solution because once it's running you keep it basically, but that's actually not the way you should work with software. So software is a constant improvement over time, and the question is how do you implement that in a sense that you can deploy software on a regular basis without changing the application all the time. What we are proposing here is we have a clear interface to the sensor, so we can have multiple sensors on the inbound side, can be our stereo-based system, can be a Basler Blaze, can be a high-resolution stereo system. Then we have basically the product side with a CAD match and also the cube, where we can basically determine the parts orientation and localization. And then we have a so-called user space, we call it, where customer software can be deployed. What we figured out in many integration projects is there comes a product from our side, we are talking about the sensor, and then there's a small little piece of software that has no place to go. It cannot go on the controller because you don't want to start implementing some stuff on the controller. On the other side, you don't have a PC available from the customer that you want to do here. So what we are adding here is a so-called user space. It's a Docker deployment that you can put on the PC that we are providing so that you can add your own stuff. There will be a project coming up where there's a motion planner included, then can be a quality inspection, but you have basically the computing area without interfering with the product side. So we have products and we have the customer specific stuff without adding an additional PC. The products can be updated in the regular cycle, and in the user space you have your own cycle how you want to do this, but it doesn't interfere with each other, so you don't have to mix different scenarios up here. How this can be done, also a GUI here, so we are always saying that it must be easy to deploy, so you can start your individual containers, you can run it. I mean, Docker is very well known, but basically it helps us here to do the individual engineering, and once you deploy this image, you're fully contained in yourself, and this works then out of the box more or less. Yeah. We are also supporting on the inbound side multiple sensors. We have GigaVision GeniCam interface here, so that's what we are doing on the inbound side. To the application side, you usually get grasp points. These grasp points are basically independent of the sensor on the inbound side. So if you decide to change the sensor, it doesn't have really an effect on the application program, because in our ways, usually the customer is the robot. The robot gets a position, and once you have this position, you don't care about the input data that you you're actually using. So you can change on the inboard side the sensor, on the outbound side basically the result stays the same in the application, which is usually the effort to integrate a new sensor, and you don't have to do this because it's already done on the software side ahead of time. The last trend, ease of use. And this is actually one of the key issues where also machine learning helps us, because machine learning generates parameters. And especially if you ever tried to configure a CAD-based matching before, you have like 20 parameters, they have to be tweaked, configured on site. This is actually what machine learning can do you with a simulation, so you get all these parameters by the neural network, so you don't have to tweak it on the GUI. This basically helps you a lot to reduce the effort for the implementation of the system, and you have it ready to use. So we are doing this on our side with a web interface, so that's in very easy access. And this means, like, for setting up a CAD-based matching, you upload a template, has been pre-trained, you press detect, and that's about it. So there's no additional parameters that you have to tweak, because this has been done before based on the simulation data that we used. The only thing that you actually add a little bit on the side is like exposure region. So basically you put it above the bin, but also this you do virtually, right? You look where the bin is, and then you set this is exposure region, and this is about it. So there's no like coding on that end. That of course you can always do this. There's an API behind, but especially if you're not interested in the coding side, you can set it up all on the web GUI and make it quite easy here. Also get access to the data, check on it. In this case, it gives you the trust in the system because you're seeing what you're doing, and that basically ends up in these scenarios. Yeah, quick use case. Why simulation helps us here. So this is one of the parts that I want to discuss here. You see that this part has a little asymmetry, which is a poka-yoke, because you want to make sure that the worker puts it in the right orientation. And now the question is for us, what does it mean for our bin picking project that this part is there, and what can we do about it? To the right hand side, you basically see the report that we are generating out of the simulation. So there are some recommendations on the sensor distance, what's the resolution we need, where to place it. This is the easy part, so we figure out we have to have the part has a certain size. We require 100 pixels on the part. This results then in the distance that is minimally there and also maximally there. And then you decide basically, okay, my robot needs a certain space above the bin, and then you go in between and you place your camera. So you just select the camera, you would say where you place it. That's the easy part. Second step is we're doing the simulation, and we are basically placing the parts in the bin and then also some other scenarios, and we are virtually detecting them, and then we figure out that we're actually seeing a large error here in the rotation. And this large error comes from the point when we are considering the poka-yoke part as being relevant to be picked from the bin. So basically, if we want to pick this part with a correct orientation from the bin, the solution actually becomes pretty unstable, because you cannot always detect this little poka-yoke part, and this leads to these large errors here in the rotational accuracy, because the parts can actually be flipped from time to time. The right column is basically ignoring the poka-yoke part in the detection. So basically we say this is actually not there, we don't care in the bin picking phase. We take it out, and then this is basically the rotation accuracy that we achieve if the part would be symmetric. And this would be the recommendation for the customer here, to say don't care about that part when you're doing the bin picking, but take it out and check on orientation later on, because doing this correctly from the bin is a high effort. It requires a lot of resolution, so to say, and actually potentially it's not needed, because the flipping you still have later on, or maybe you don't even interested in that. This helps us in the simulation, so we figure out symmetries from the parts, and we can say if some of the things are in there and you need to consider them, discuss with the customer, say, is it important for you that this symmetry is considered or not? And based on that, you make a decision to do it in one step or two. And this is basically something that you potentially would have figured out on site when you start setting it up. So here in the simulation ahead of time, you get all this information, and then basically ignoring that makes the solution a lot more robust. Then we can still run all this also in simulation on the sensor, so we can set all our sensors to simulation mode, so we can also upload virtual scenes. So basically we generated something, the customer wants to see it on his device, we can do that. So it also helps to show basically the improvements that we made over time. And also the full system is remotely accessible, so you can also get everything from the customer, which helps a lot, especially in the last 2 years, to maintain systems and to also support them without going on site. Because with the simulation in the background, we can always cross-check what actually happened on the customer side and identify the gaps in here. Coming to my summary of the talk, so I introduced 3 major trends here. So one of them is focus on the good data. So most roboticists have the model data available. So in my opinion, there's no reason to learn kinematics because that's something that's model-based. So it's the same applies if you have CAD models already, use them for the training and don't start all over again if that didn't exist. So basically whatever model data is available, use it and use the things that are actually trustworthy. So the data that you labeled yourself, the data that you have, because whatever happens later, you will never figure out. Have a scalable software platform, so there's a lot of software engineering usually needed, and the question is separate product from project. So we have the product side, that's standard, that's not going to be changed, and then we have the project side and try to bring it on the same PC, because otherwise you have like in the end 2 to 3 PCs that you have to bring together. So that's the way we expect here. And then last is enable ease of use. So basically machine learning can help you to reduce the amount of parameters unknown, the one that are hard to tweak. And basically this is why actually we are using it, as it's ease of use. So basically not so many parameters for the customer. Yeah, that ends my presentation. I hope you enjoyed it and I'm looking forward to your questions.